I can't possibly say enough things and give enough credits. These are only a few of my colleagues that have been contributing over months and years that have led to this point in our research. Big Red and Big Red 2 are machines, for those who don't know, that Indiana University is very fortunate to have. They are absolutely first-rate, high-performance computers owned by academic institutions. They're on the order of about a petaflops capability. Now, in fairness, today, the largest machine in the world, and I can even say machines, belong to our colleagues in China. I'll mispronounce it, but Taihu Lite, for an example, is nominally 100 petaflops machine, plus or minus a few percent, depending whether you're measuring at its peak or as against a LINPACK benchmark. But it is a worthy question to ask for a university in the US to truly maintain its premier leadership in academic computing. How are we going to move forward over the next few years or decade? And so what might in 2030, and I'll be thinking about retirement then, what might in 2030 the performance be? And I will tell you frankly, if our research is successful, the likelihood, and this is a conservative estimate, will be on the order of an exaflops, or 1,000 times the performance that we have today. But in between then and now, there are really big problems that the whole field is facing. And I group these into two groups. One is in the technology bases that are required, including Moore's Law, which we've been writing for 3 decades plus to allow ever more dense devices on a die, the Nard scaling, the form of parallelism we exploit out of a processor core, issues of power, which are at the point that if you were to turn on and off every transistor on a die that's possible, you would have the heat density of a nuclear reactor. Not an exaggeration. I wonder what the problem with nuclear reactors are, but that's not my field. And then in addition, because of the power, the clock rate that we're no longer able to exceed. The other bullets, which I won't read, are requirements that we have today to make these things better and more useful for the future. Now, if we look at the classic top 500, this is provided to me by my colleague Eric Strohmeyer at Lawrence Berkeley National Lab. We see this, roughly speaking, exponential growth where the red sawtooth curve shows the #1 machine measured by a LINPACK benchmark since the early 1990s. And the extrapolation, let's see if I can do that, of noting that the curve is beginning to flatline. Indeed, this is slightly old, and we're having the same problem with the number 500 machine. There's usually a variation of about, I can't even read it. Oh. However, in fact, it's really a 3-curve area where the mainstream all is within about a factor of 4 performance, while these really high-speed machines are relatively few. IU is well positioned because of that. We are at the top of the mainstream. This is exactly where you want to be, the knee of the curve in terms of performance. This curve, I actually got this from the late colleague Burton Smith, who passed away only a couple of weeks ago. We see all of the things that used to contribute to our advantage in performance to be flatlining. Here at IU, both between computer science and the intelligent systems engineering, we have 3 interrelated projects in the computing paradigm, runtime system software, and parallel architecture. I've associated professor names there. And this slide shows you on the architecture area, a new non-von Neumann, not standard approach in which we have determined that a tremendous amount of growth in performance and improvement in such. Here, for an example, is a diagram drawn to scale, whatever that means, 400 square feet. Today's largest machine in the US, Titan, at Oak Ridge National Lab, takes up over 4,000 square feet. And this is about 100 times that performance. These are the technologies that are being developed at Indiana University and SAIS. Thank you very much.